Hi, Christian. We hope you're feeling okay. We're going to get started with our lesson for today, which is on combustion analysis. So we're going to be getting the empirical formula from combustion data. And if you forgot what combustion is, the AP students just wanted to show you what you're missing today. Ready, guys? This is what combustion is. Oh, look at us lighting matches and having fun in chemistry. Don't burn each other's hair. Woo! We wish you were here. Oh, that wasn't nice, was it? Okay, blow out your matches and don't set your notes on fire. Okay. Okay, no more matches. No more matches now. So, hopefully you've come off your medication. We're going to learn how to calculate the empirical formula given different data. So instead of giving the percent of each element in the compound, we're going to be given data from combustion. What you need to know about combustion is that it is the reaction with oxygen. So oxygen is always a reactant. Okay? In a combustion reaction, you need oxygen. And when you're combusting a hydrocarbon, or at least substances that have C and H in them, you always make the same two products. You always make carbon dioxide, and you make water. I'm just going to write H2O because I'm running out of room. So we're going to particularly be focusing on the combustion of either hydrocarbons or CH and something compounds. So we're going to have C to the A, H to the B, and some element X maybe. And our job is to figure out, based on how much carbon dioxide and water we generate, based on what the initial formula of our compound was. Okay? So what they do is they take some unknown thing that has CH and maybe something else in it, and they burn it. And they collect what comes off of it. And based on the amount of products that you receive, you can figure out what the initial formula of your compound was. Remember, the whole goal, in order to get the compound, just like we did with the other things, was finding moles, right? So that's going to be our whole goal here. So first thing you're going to do is write a generic equation for the combustion reaction. You won't be able to balance it because you don't know the subscripts of your hydrocarbon. So it's a generic reaction. So it will be something like C to the A, H to the B. That would be if it's just a hydrocarbon. If it contains some other element, then you would include your other element. Okay? But if it's just a hydrocarbon, it would be that. And maybe you'd have some other element attached, maybe not. Sometimes you might have oxygen to the C, nitrogen to the C, sulfur to the C, something like that. And it's combustion, so it's always reacting with oxygen. And you're always making carbon dioxide and water. So it'll look something like that. They're going to give you the mass of carbon dioxide. So you're going to convert that to moles of carbon dioxide and then moles of carbon. Okay? So given the grams of carbon dioxide, so let's say we had 5 grams of CO2. Just making that up. They'll tell you what you have. A lot of times they give it to you in milligrams. So you'll have to convert it from milligrams to grams and then to the formula mass. So we'll go to moles of carbon dioxide first, and I will walk you through an example. Okay, 1 mole of carbon dioxide is 4401 grams. It's formula mass. And then, now, I think the question became, how do you convert that to moles of carbon? It's kind of like atoms of carbon. How many moles of carbon are in one carbon dioxide molecule? How many carbons are there? 1. So 1 mole of CO2 always contains 1 mole of C. That is the format you're going to use to get to moles of carbon. And that's a number you're going to need, so you're going to have to write that number down, okay? Yes, even though you're multiplying and dividing by 1, you still need to show this last step. You still need to show that, look, we had moles of CO2 and now I have moles of C. You still have to show that you know that relationship. What's wrong?
So it just changes from CO2 to C?
Well, it doesn't just magically, okay? It does. We have moles of carbon dioxide, and then what you have to recognize is that, say you had 2 moles of carbon dioxide, there would be 2 moles of carbon in that. Because in every 1 molecule of carbon dioxide, there's only 1 carbon. So whatever your moles are of the carbon dioxide, that's also equivalent to your moles of carbon in that compound. But if it were oxygen here, I'd have to double it, right? Okay. After you have your moles of carbon, but you need that number, so write that number down. Then you're going to convert it to grams of carbon. So you're going to convert your moles of carbon to grams of carbon by multiplying by the atomic mass of carbon. So you're going to take your moles of carbon that you have, and remember 1 mole of carbon is equal to 12.01 grams. So that will give us the grams of carbon in the compound. Make sure you label everything. After you do that, you're going to use your water data. You're going to take your grams of water, convert it to moles of water, and then to moles of H. Just like we did with the carbon dioxide. So we'll have, let's say we have 5 grams of water. I don't know, 5's in my brain today. You're going to convert that to moles of water. That's why last night's homework was so important. 1 mole of water is 18.02 grams. That's its formula mass. That'll give you the moles of water, but you really want moles of, Bryce, stop playing with matches. You really want moles of hydrogen, okay? According to our formula, in every 1 mole of water, there are, how many moles of hydrogen? 2 moles of hydrogen. But the mistake you just made, Leah, is a mistake that's made all the time. Yeah. Okay? Because we're so used to with the carbon dioxide 1 for 1, we do that here. But it's not. It's 1 for 2. And that'll give us our moles of hydrogen. Okay? And that is a number that we need to write down. After we have the moles of hydrogen, we can go ahead and convert that to grams of hydrogen. Okay, and again, we would just take our moles of H, 1 mole of H has an atomic mass of 1.01 grams. And that would give us our grams then of hydrogen. Okay? Now, if there's another element involved, then we're going to have to work through some subtraction with this. And I'm not sure if we have this in our notes or not. Do we have another step? Yeah, okay. Good. I think it might be on the next page. Yep. Okay. This is really step 6, okay? If oxygen is the 3rd element in our compound, then we'll get the grams of oxygen. This could, though, really be or whatever. Whatever element is attached. Most of the time it's oxygen, but it doesn't have to be. So think about what we know. I just have to take us back to that reaction for a minute, and then we'll walk through. I promise we're going to walk through a practice problem with this. We now know the grams of carbon that were generated in carbon dioxide, the grams of water that were generated in, hydrogen that were generated here, right? What you have to recognize, God bless you, is that all the grams of carbon that are in carbon dioxide that's produced are equal to the grams of carbon that were present in your original compound, right? So the moles of carbon that showed up here are equivalent to the moles of carbon that were originally here. And same thing for hydrogen. The moles of hydrogen that appeared here are the exact same number of moles of hydrogen that were present here. But for oxygen, we can't, bless you, for oxygen that's not true. we can't say that the oxygen here and the oxygen here all should add up to the oxygen here. Do you know why? You're burning it and adding in more oxygen, right? So we have to get the grams of oxygen that were present here a different way. We can't do it the same way we got the carbon and hydrogen. But how are we going to do it? Well, here's how we're going to do it. They're going to give you the mass of the whole compound. You just figured out how many grams of this there were, how many grams of this there were. So we can get the grams of oxygen by just subtracting, right? The leftover mass. So, to get our grams of oxygen, we will subtract the mass of the whole compound minus the grams of H and the grams of C. So the mass of O equals the mass of the compound minus the mass of C and the mass of H added together, right? You add those up and subtract, and you'll get the leftover mass, which is due to oxygen. Then, remember, the whole goal isn't to get grams. The whole goal is to get moles. We have our moles of C, our moles of H. We'll convert this to moles. This is the page long. Convert the mass of O to moles of O, or whatever. It might not be O, it might be N, and that's okay, right? So you'll have your mass of oxygen, and you'll convert it to moles by... let me do grams here. 1 mole always equals the formula mass. Okay? That'll give you your grams. Now, we are at the same place we were when we had moles of every element in a compound with percentage data. What did we do to get the formula once we had moles of everybody?
Divide by the smallest.
That's next. Divide by the smallest moles. Divide C, H, and O by the smallest moles to get some subscripts. And just like last time, if your subscript's not a whole number, you have to multiply it and everybody else by something so that you get a whole number. And then that is your empirical formula. I don't think I wrote anything else. Yes? Okay, so I'm gonna stop this one and we'll save this one, Christian, and then we'll do another one with the practice problem.